Hey guys, so welcome back to lesson 4. Last lesson in lesson 3, we talked about the properties of liquids under the kinetic theory. And so now we're going to get a little deeper into that, and we're going to talk about vapor pressure and boiling point. So let's go ahead and get started with that. So after today's lesson and throughout the lesson, you should be looking out for these things. So our goals for this lesson is to describe vapor pressure and how it's affected by temperature and the nature of the liquid. You should be able to explain the relationship between boiling point and vapor pressure, right? You might have a good concept of what boiling point is, but maybe not what vapor pressure is just yet. So we're going to take a look at that. And you're going to be able to predict a way to boil a liquid without changing the temperature of the liquid, which might sound a little bit crazy, right? Like how would you do that? But you're going to be able to predict a way to boil a liquid without changing the temperature of the liquid. So let's go ahead and get started. Exciting stuff. So first thing we got to talk about is vapor pressure. So vapor pressure, also known as VP, that's the abbreviation, is the pressure caused by the evaporated particles in a closed container. So we talked about last lesson how there's that equilibrium in a closed container. Liquids are changing to gas particles. Gases are changing back to liquids, okay? So any of those liquids that are changing to gas particles, right, are contributing to the gas pressure building up inside that closed container. And since we call that gas a vapor, that pressure that builds up in there is called vapor pressure. So with the lid, the vapor will be steady, so the pressure can be measured. We can actually measure the pressure inside of a closed container. And without the lid, the particles will diffuse. Okay, this is back in lessons 1 and 2. But remember, if you let a gas escape from any container, that is called diffusion. So one more time, vapor pressure, it's that pressure of gas building up inside that closed container. So as temperature increases, vapor pressure will increase. So we have another direct relationship. Okay? So as temperature increases, vapor pressure will increase. This occurs because more particles have the energy needed to evaporate. And like I said, this is a direct relationship. So as you increase the temperature, you are increasing that kinetic energy, and that means more of those liquid molecules can turn into gas particles, and that means you have more vapor pressure, right? If we're adding more molecules into that area, there are going to be more collisions and the pressure is going to be higher. So all related in here. Next up, let's talk about what vapor pressure has to do with IM forces, intermolecular forces. So as the intermolecular forces in a liquid increases, so those attractive forces between the liquid particles, as they increase, the vapor pressure will decrease, right? The more sticky those liquid particles are, the harder it is to get them to change into a gas. So if they're not changing into gas particles, really that vapor pressure is going to decrease. Everything's going to want to stay a liquid, nice and sticky. They have high intermolecular forces. As the forces of attraction are stronger, it is more difficult for particles to break free. Okay? So as the forces of attraction are stronger, it's more difficult for those particles to break free and turn from a liquid to a gas. And there is an indirect relationship here. So as those intermolecular forces increase, vapor pressure decreases. There's that indirect relationship. So we just talked about this, but strong attractive forces, right? The more sticky your liquid particles and molecules are, we're going to have less evaporation of those particles. So the intermolecular forces restrict the movement of the molecules. So let's go ahead and talk about boiling point now. We just talked about vapor pressure. Vapor pressure is just that pressure that's building up inside of the closed container when the liquids change to gas, and you have that pressure of gas building up in there. So let's talk about boiling point. Boiling point is the temperature at which a substance will boil. And boiling is a conversion from liquid to gas throughout the entire substance. So recall that evaporation is a conversion from liquid to gas at the surface, right at the surface where we have high kinetic energy, those are going to evaporate. But boiling means we're going to turn up that temperature, we're going to add increased kinetic energy to all levels of the liquid, not just the surface. So all of those molecules are going to want to turn into a gas. So in order to boil, your vapor pressure must be the same as the atmospheric pressure outside. Okay, one more time. In order to boil, your vapor pressure must be the same as your atmospheric pressure. So let's talk about normal boiling point. So the boiling point at a standard pressure of 1 atmosphere. So we have a standard of 1 atmosphere, and if we have 1 atmosphere of pressure, okay, we have a normal boiling point. If not at sea level, you will not see the normal boiling point because the atmospheric pressure will be different. So boiling points of substances are different depending on where you live. If you live super high above sea level, it's going to be a different boiling point than if you live below sea level. Okay? But at 1 atmosphere, at exactly sea level and 1 atmosphere, the normal boiling point for water is 100 degrees Celsius. So just like I said, boiling point is not constant, and it depends on the atmospheric pressure. Where there's a high atmospheric pressure, boiling point increases. And where there's a low atmospheric pressure, boiling point decreases. So let's try and remember, when a substance is boiling, temperature remains constant. In any phase change, temperature is constant. So we're going to turn up the heat for boiling point, but we're not gradually increasing the temperature as we go on. We're going to turn that stove on to boil, and it's going to stay at that temperature. Okay? And all of those molecules are going to get to that temperature. It's going to remain constant. At the boiling point, the added energy from that heat goes toward changing the liquid particles to gas particles instead of increasing the temperature. Okay, so you might be thinking, where's all that energy going? It's going to convert the liquid to gas. It's not going to raise up the water, right? You can't burn water. And next, boiling can also occur by lowering atmospheric pressure until it equals the vapor pressure, like in a vacuum. So you can boil something if you lower its atmospheric pressure enough to where it equals the vapor pressure, and it will boil spontaneously. So you have this curve, okay, in your notes. Let's go ahead and take a look at that. Starting on the left side, we have sea level. Sea level is 1 atmosphere, and that is our normal boiling point at 100 degrees Celsius. Okay, now let's travel along. Let's look at what's happening below sea level. If you are below sea level, your atmospheric pressure is going to be higher. If your pressure is higher, that means your boiling point is also much higher. Okay, so below sea level, if we have 1.5 atmospheres, our boiling point will be 110 degrees Celsius. This is because it takes more energy to have the vapor pressure equal the atmospheric pressure. So a higher boiling point is needed. Okay, higher atmospheric pressure, you need a little bit more energy to get those liquid molecules to turn to gas and make the vapor pressure equal the atmospheric pressure so we can boil. And one more over, let's take a look at that big mountainous area, right? That big curve. So what happens above sea level? At above sea level, you have less atmospheric pressure. The air is nice and thin up there. So with less atmospheric pressure, it takes less heat and energy to make the vapor pressure equal the atmospheric pressure. And that means your boiling point is lower. So it's about 90 degrees Celsius if you have 0.8 atmospheres. And of course, these can widely change. Okay, you can live at a sort of medium between below sea level and above sea level. Okay, you can live at any sort of altitude. So depending on different regions of the earth in which people live, there's different boiling points and different vapor pressures, different atmospheric pressures. And this is a big challenge to people like pastry chefs who make things like chocolate or need specific boiling points to make sugar candies with. Okay, because if you travel to a different country to go give a presentation or go cook at a fancy restaurant that you've been invited to, you may need to switch up what you're doing because the boiling points and the atmospheric pressure and everything are different. It can really ruin this recipe that you've created. So a lot of pastry chefs study chemistry, and especially this type of chemistry, so they can make sure they know exactly what they're doing before trying to make really amazing things, um, and then it all comes crumbling down because they're at the wrong boiling point. So if you have any questions, let me know. Hopefully this wasn't too bad. Not too many calculations in this one, but a lot of conceptual things, a lot of new things to think about. So if you have any questions, hit me up on Teams. Good luck on this next homework. It should be pretty straightforward if you're using the notes, and I will see you in the next one.